anyway. What we can be more sure of is the actual bandwidth of the hardware of the physical front end, because physics is physics, and we can see these things and measure them more easily. They claim 100 megahertz on the scope, and they include a 100 megahertz probe, at least in 10 times mode. So if we take our bandwidth of the entire system, since these are cascaded, we're just doing 100 and 100, which means that we're going to result around like 70-ish, a little more than 70 as far as our bandwidth goes. Unless they're saying they're giving you a higher bandwidth with the hardware than 100 megahertz, and then that would even it out with the 100 megahertz probe, but it'd have to be like 350 megahertz or so to start to make that negligible. Or they were artificially increasing the gain above certain levels, which is also possible trickery. Which is consequently why you see me using a fixed 1:10 ratio 250 megahertz probe with my 100 megahertz scope. But noob information here, as soon as you flick that into 1 times, bam, you don't have a 100 megahertz probe anymore, you have much lower. So they say about like 6 megahertz, now that depends, and the only way you can really know is through testing. And unfortunately, my 250 megahertz probe does not fit in the case because of this goofiness. Now, I could take it apart again and use that for testing, but I can't be bothered. So, bandwidth. Let's talk about bandwidth and signal recreation. So bandwidth, we're really talking about something different when we're discussing analog signals and sine signals versus digital signals and square signals. With sine waves, you're much more interested in the point at which that starts to become attenuated as far as the amplitude, and that's what we can call bandwidth. But that relates to the speed of the scope, as in the sample speed of the scope, which relates to rise time, which is how quickly it can detect the change in the rising voltage, so you get a nice square leading edge on your digital signal. To represent this visually, I am going to use a digital audio workstation and apply an EQ filter to it so you can see what I'm talking about. Now I'm just going to open up Audacity, which is not a workstation, it's a wave editor, but you can use it to generate test signals, so I'm going to generate a 1 kilohertz square wave. Then I'm going to dump it into Logic, and as you can see, there you go, as square as it gets. Now, the channel EQ has a built-in FFT function, so you can see the harmonics right here. Fundamental harmonic is at 1 kilohertz, and then we just have odd order harmonics going up. For measuring purposes, we will also be concerned with the even order harmonics, but this is a symmetrical signal, so we're just going to get odd stuff. That's music crap. I won't deal with that right now. Unfortunately, we don't have a built-in waveform viewer, so let's just head over to Google and see if somebody maybe adapted some old sample code. Let me see, Waveform Demo. Go over to this tab and, oh, hey, Alex Kennis. I bet that's a really smart and attractive man who decided that the world needed a free version of this. So let's see what he has to do. Well, it looks like I already have this plugin installed from this very humble creator. If only he weren't so lazy, though, he may have programmed a automatic trigger in here, but he didn't. He decided just to put a sample hold buffer function on it, so that'll work just as well. Maybe that was already in it. I don't remember. It was a long time ago. Now, the EQs on here, these are all going to be 6 decibel an octave slope because they're all like biquads, so what are you going to do? Speaking of biquads, oh, look at this. That same extremely humble inventor put a biquad coefficient calculator in here that you can run right inside your digital audio workstation. If only there were a way to send him money for all of his efforts. Look in the video description for support links. So what I'm going to do is sweep the -3 dB point closer and closer to the fundamental, thus attenuating the upper harmonics. And as we see, the waveform changes. As we start up over around like the 8th, 9th, 10th harmonic, the wave looks pretty square. But as we get closer and closer to the fundamental, it's shaving those harmonics off and changing our square wave into a sine wave. And as we get down to where the -3 dB point is affecting our fundamental frequency, it's going to change the amplitude of the wave altogether. Now, this is how our bandwidth is affected by anything beyond a sine wave. So as we saw with regular math tricks, you can recreate a sine wave pretty easily just at our Nyquist frequency, but we need more sample points in order to figure out if that's square or triangle or sawtooth or whatever. So getting into our Fourier series. Now, this is going to get a little bit math heavy, but it's easy math, so don't worry. So as I said, if we had a pure sine wave going to this, we would just see a spike at 1K, but since it's square, we see the upper harmonics. And the more harmonics you have, the more square that wave is going to look. So right in the middle of recording this, my phone decided to start randomly playing a Hope for the Dying song. It always either plays Hope for the Dying or The Burial, just randomly. I found the correlation, though. Elisha Mullins is haunting my phone. Don't let the face paint fool you. He's a really cool guy. But still, get out of my phone. So I looked for some online examples so that I wouldn't have to go through all this myself, but I didn't really find any. If you go over to a Recordingology, they give you some of the equations and how that applies in like an audio, from an audio perspective. But they do give some nice diagrams of like the decaying harmonic series and the representation of the waveforms. And she, he, they, whoever pointed out that if you want a perfectly square wave, you need a infinitely wide bandwidth, i.e. infinitely fast sample rate, and we don't have that. Actually, we need an infinitely wide bandwidth times 2 because we have an infinite Nyquist point. Just kidding. Now, if you don't use Wolfram Alpha, get with the times! But you can use it to graph some of these functions and then twiddle around with the equations and see what waveform comes out of it, but I'm going to use something else. So let's talk about the math first. And I told you this math is going to be easy. If we want to build up this equation, basically we're just stacking sine waves. So let's do it out to 3 harmonics. We'll just do sine, 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 and then each of them is going to be sine of something. And we're just going to we're going to represent our odd harmonics, the first couple. So we're going to do sine, which is our fundamental, and then sine 3, which is our third harmonic, and then sine 5, which is our fifth harmonic. So that's just sine 3x over 3, sine 5x over 5. Now, if you want to draw that in a way that the particular calculator I'm going to use will recognize it and do anything coherent, we have to kind of rejigger the equation a little bit, but don't worry about that. And I'm just going to use the graphing calculator thingy that's built into Mac OS. And if I paste that in here you can see 5 harmonics. This is the representation of a waveform that we get. So this is as square as it's going to look up to 5 harmonics. And if we just copy paste that, we could just keep adding on harmonics willy-nilly as much as we want. 7, 9, 12, whatever. So if we go in here and we look at 7 harmonics as opposed to 5 and then graph that out, this is our result. So as you can see, as we go up, it gets more square. Let's do it with the 9th harmonic. Surprise of all surprises, it gets more square. Now, as far as these little horns on the sides of the waveform right here, that's called the Gibbs Effect, and that's where math magic comes in, those little boxes that I talked about earlier. So anyway, let's look at what happens if we only have 3 harmonics, which is kind of the minimum if we want something to look kind of square wave-ish. This is what it is. And then we'll build that up 5, 7, and now 9. Consequently, I love this kind of program, man. I still am old enough to have had to do the hand math, and like we can take an equation and integrate, differentiate, whatever. Obviously not this one because it'd be a mess, but that's calculus right there, and I didn't have to write a single freaking Greek character. I suck at calculus, but with this kind of crap, you can do it every day and not even think about it. So yeah, bandwidth, that is where our frequency response is down to half power or down minus 3 dB, blah, blah, i.e. 0.707 or 1 over the square root of 2. That's just industry standard. It's nothing set in stone. If you want to learn about why that is, you can look up the additional math online. What you can also look up online is a harmonics calculator. So this ain't just for music. If you look at something like 1 megahertz, then obviously the harmonics are going to fall evenly above that. But it gets more complicated when you get to like 7, and it's convenient to have a calculator here. So that way you can match your minus 3 dB up with your frequency and know where you're going to be cutting into it and turning that square wave into a sine, or when you're going to start decreasing the amplitude of your signal. So you know you've hit your bandwidth when you're scoping a signal or probing a signal, and you see that you have dropped down your amplitude by 0.707 from what it originally was at the fundamental, but that's for a sine wave. So again, your square wave is going to round off to a sine, and then when you hit your fundamental, you're going to start decreasing in amplitude, and you'll get incorrect amplitude measurements. And generally, like seeing up to the 9th or the 10th harmonic, like that would be fantastical, right? So if we say we want to be able to see the 10th harmonic and we have a 70 megahertz bandwidth limit here, we can see down to like 7 megahertz or something like that. But that changes, of course, if you say like, well, we're fine with going through like the 5th or the 7th harmonic for square waves. Or again, if you're just looking at sine waves or sinoids of some kind. So let's see, they did pull some magic, and it's 500 megasamples a second, right? Best we can hope for if we want to see the 7th harmonic is being able to see out to 70 megahertz. Now that's going to be attenuated by 3 decibels because of the probe that's included, assuming there's no trickery going on with the gain levels. But if you get like, 350 megahertz probe or something like that, you should be able to see out to the 7th harmonic. If it's actually 250 megasamples a second, I said 250,000 megasamples a second, we can expect to go out to like 35, 36 megahertz, something like that. And at 250 megasamples a second with a sine wave, the Nyquist frequency is 125, so we're capped by the front end, theoretically. And if you have the probe, you're never going to get there anyway because you're limited to 70 megahertz. Visual demonstration time. Now, let's see what that looks like. As in, like, losing upper harmonics and rounding our square wave off to a sine and then losing amplitude. We can see right here if I take a square wave and sweep it up in frequency and feed that into the front end of my ancient 10 megahertz hobby scope. As I turn the sweep knob back and forth at like 10 megahertz or something, like I don't remember what this is, you can see the wave changing in amplitude and changing in shape as well. Let me show you that a little bit easier way to see with analog scope tricks. I don't know if you could do this on a digital scope. Somebody let me know if they know how to do it. And again, the right third of the CRT is messed up on this scope, as I mentioned before, so just ignore the distorted squiggles on the right side. So instead of a sweep, I'm going to use a stepped signal, and I just took my ugly blue pill square wave generator, the Arduino sketch, and cycled through from like 2 megahertz to 5 megahertz to 10 megahertz to 18-ish megahertz, and then fed it into one channel of the front end of a 100 megahertz oscilloscope that also has 20 megahertz bandwidth limiting, and fiddled with the trigger until I got them all on the screen at the same time. Now, obviously, if I were using a higher bandwidth probe, these would all be square waves, but you can see they're rounding off because I am using a probe with a limited bandwidth. Also, if I pop in the 20 megahertz filter here, you can see that the amplitude of the higher frequencies, waveforms, are lower than they would be if I disengage it. So it's pretty easy to see us both losing our upper harmonics on our square wave and also losing amplitude because we're cutting down the fundamental below those harmonics. And if I run this same series of step signals, I almost said step sticks because I have 3D printers on the brain. Anyway, if I run the same stepped signal into the front end of my 10 megahertz scope, obviously running from 2 megahertz to like 20 megahertz is going to clobber this front end, and it can't keep up speed-wise. So even on the 2 megahertz signal on the 10 megahertz scope, we're going to be rounding off our square wave, and you can see the drastic change in amplitude when we go up to 20 megahertz. And this segues very nicely out of our theory segment and into our, or back into our handheld oscilloscope. So digital storage oscilloscope, this is what it boils down to for me. You have 3 factors here, working down from 3 to 1, oscilloscope, we know that, 2, storage, and number 1, digital. So as far as like the digital oscilloscope part, like I can take it or leave it. I'm fine with the analog stuff until you get up to like super high bandwidths. But the joy of digital scopes is like the triggering tricks and the digital decoding and all of that kind of stuff. That's when I was talking in the previous video, and I will talk more in the future about criterion for selecting a scope. And we're talking about like new and digital versus like old and analog. Like, do you need the digital functions? Do you need extremely fast rise time? Do you need like 2 gigahertz of bandwidth? Do you need digital logic and decoding, or do you have a logic probe? Do you need the digital multimeter functions, or do you have a digital multimeter? Do you need to interface it with other digital gear and dump the information that's on that into some kind of format that makes, you know, charts and graphs and you can export to programs and things like that? If the answer is no and you just need to see waveforms, well, then you really cut into some of the benefits that I perceive to be advantages of the digital scope when you're walking in that domain. If you just need to see the squiggly lines, it doesn't matter. Number 2 is storage. So being able to snapshot your waveforms, store them in the scope, and pull them up and manipulate them later on, or export them as photos or whatever you're going to do with them. And then number 1 is the actual functioning of the wave drawing, squiggly wave drawing oscilloscope part of it as it pertains to the settings you're allowed to get to. Also, when you move into the digital realm, a lot of things that will be complicated and expensive to do in hardware, you can do in software and have the flexibility of like adding features if there's something there's not there that you need or would like or would make your life easier. But this all comes down to the skill, the forethought, and the ability of the programmer. And as we mentioned with this particular scope, it's not open source yet. Because the hardware is here, the firmware is lacking, and there are clever people out there. Just saying. So what you get is what you kind of get until someone figures out how to unlock these and flash some new firmware on there. Walking through the features of this particular wave wiggler, if we look right here, we can see what we may be limited to. Now, we do have our mode button, which is just being able to move the cursors around and being able to change the scale back and forth centering on the wavelengths. Okay, fine. We can go in here, and then the back and forth cursors, they affect our X and our Y axes, which is kind of like a quasi zoom function, and there's no actual zoom function, which seems like it would be something that's fairly simple to add. So up here you see in 1x we go from 10 volts division to 5 to 2 to 1 to 500 millivolts to 200 millivolts to 100 millivolt, and that's where it stops. Now when we switch our probe over to 10 times, you can see that it jumps up to 1 volt. Then we go down to 500 millivolts, and that's all we get. If you go the other direction, we go all the way up to 100 volts, which means we can do much higher voltage measurements, but we lose our low voltage testing, which means 500 millivolts, you're pretty limited in what you can do as opposed, or as it pertains to like low level signals. Now, getting into complaints about like the digital stuff, as far as like the shapes of triggering we have, there's only two options. There's leading edge and there's trailing edge. There's like no blanking, there's no PWM, there's no anything like that, which are options that you could add in the software, but they opted not to. As far as the trigger itself, we have single mode, normal mode, and auto mode. So auto works as you would expect-ish, and then normal is a little bit sketchy. You go through and you can adjust the point with the right cursor here, just like you would expect to be able to do. But you can't really fine-tune the timing, you can't fine-tune the slope or anything like that. Like I said, what you get is what they decided to build into it, and as far as I see, there are no options for that. And then the single trigger doesn't really seem to behave like I would like. It seems to miss samples up front and then just trigger somewhere in the waveform that it thinks you would like to trigger. I guess maybe it guesses halfway through or something like that. But as far as pulse things, there's very little you can do about it. Now, I do suspect some of that comes down to the hardware and how they have the ADC clocked and when it's taking in samples and when it isn't, because also built into the firmware, you change your sample resolution or your sampling speed depending on some of these other measurements. So when you're in 10 microseconds, so when you're in the very low time bases here, and this can go down all the way to 6, which is very nice, and you can go all the way up to, I think, 60 seconds or so, which puts you into slow mode, which is also very nice. We have additional times available to us. This is slow scroll mode, so it goes all the way up to 50 seconds-ish, which is nice, but a little bit weird that they lock you out of some of this stuff in the other modes. Now, I have been able to trick it and get some of the resolution, the 50 millivolt resolution of 1x mode, by putting a 10 times probe in and switching it to 1x mode. But of course, then all of your math is wrong. And depending on how zoomed in you are on the waveform, it does the math strangely. Plus, seemingly, and I know this is getting into more review stuff, furthermore, the frequency stuff works in some modes and not really in others. And when you're in the long logging mode, it doesn't seem to be able to center the cursor over a particular peak and get the amplitude there. And when you do, it could be goofy when you zoom in because it changes as opposed to when you zoom out. And one thing I really like about digital oscilloscopes and transition period oscilloscopes is when you can have the X and the Y cursors that you can actually move to measure the amplitude and the wavelength, as opposed to just trusting the automagical stuff, because that depends on like a continuing cyclical pattern. But if you have something that's uneven, it's nice to get in there and be able to measure it. Now, maybe that's kind of what it's doing when you zoom in and just see part of the waveform, and the amplitude seems to change as well as the frequency, but I couldn't find reference to that. And that's not what I want. I would want to be able to measure it no matter how far out or in I'm zoomed, because we don't have a proper zoom. And furthermore, when it comes to going into viewing our waves, we can pull up something like this, take a look at it, but then when we go to use any of our modes here, these are replaced with delete buttons, which is whatever. But there's no zooming in, there's no zooming out, there's no seeing what's going on with it. Because we just basically take pictures of the waves. There's nothing that we can do about it. And when we don't have little reticles or markers that we can zoom in and look to measure time where we want it and measure wavelength and amplitude and things like that, basically you just have a picture of your waveforms, as far as I can tell. Again, didn't do any in-depth testing. This was just from like, a cursory half hour with this thing. But I did just run some signals through it and like willy-nilly plug in different types of probes just to see what was going on there. So here's an 8 megahertz square wave with the included probe in 10 times mode. It's pretty much what you would expect. Same deal when we switch to 1 times probe, because obviously we're losing our bandwidth there, so we're rounding off our square wave a little bit, and it seems to make it look as though it's a pulse or has a different duty cycle. It actually doesn't though, which is a little strange. Plugging in just some clip probes with a BNC connector, you can see right here what the waveform looks like. Again, what we would expect. Again, as far as like an uncompensated, unterminated probe without like 50 ohm wire. And speaking of 50 ohm wire, this is some RG58 that's just soldered right onto it in 1 times mode. This is a DIY probe with a 50 ohm tip on it. The negative goes to the shield, which is RG174 wire. This was based on a passage from the Handbook of Black Magic. That goes to an RCA that has a 50 ohm terminator inside it, and then that's adapted to the BNC connector. So this is what that looks like in 1 times mode. Now, of course, this is going to be like a 1-to-2 divider, and there's no capacitive compensation, so this is what we would expect, in addition to the voltages being off. Then we have the totes not janky patent pending passive differential isolated Probotron 5000, or Dip 5000 for short. Yeah, it's basically just a Ballon kiss my butt. Not quite as nice as my custom-built RF Jankomatic 4000. Consequently, winding number 38 wire onto these freaking binocular ferrites is not something that I like doing anymore. It was pretty annoying. 2 out of 5 stars, would not wind again. Then we have the Dip 5000 with the optional, oh my god, where the heck are my 50 ohm pass-through terminators? I'm recording a freaking video, I don't have time for this crap attachment. So yeah, there you go. Waveforms from a couple different probes running into a couple different modes, and a little glimpse into my world of electronics hell. So this is a 3-volt signal sent in through the regular probe. This is in 1 times, and as we can see right here, the voltages are shifting around, that type of stuff, and we're losing our squareness of our wave due to the limited bandwidth. And then if we go to 10 times mode on the probe and switch this over, then you can see what we have right here. For some reason, the voltage measurement is closer than it was before, but we can't go down any more than 50 millivolts. So if this were a signal from a power supply and I wanted to measure, for example, like the ripple and the noise, it'd be very difficult to do without being able to take a 10 times probe, stick it on there, and then blow up the signal so that, we can see all the tiny little ripples. Now, as you can remember from a previous video, I mentioned that my analog scope behind me has a 500 microvolt setting for the vertical division, and it has amplification from there for 10 times. So we can get right up in there on the wave, zoom in like crazy, and really see what's riding on it. Zoom, enhance. Zoom, enhance. Zoom, enhance. I mean, we could get to the same level if we had 60 decibels of gain flat to 100 megahertz, or at least 20 megahertz if we want to meet the measuring specs. So good luck with that, and Godspeed with your PCB. Send me one when you're done. Now, as you recall, I put out that video on overclocking pill boards in Arduino IDE, and this is ultimately what I was trying to use that for. And I managed to make a square wave generator that was amplitude constant and varied in the frequency up to around like 60-ish megahertz or so. And then to supplement that, I made just analog oscillators. It'll go up into the VHF range with a fairly consistent sine wave, but as it turns out, I didn't even need that, and I'll show you why. This is what a 20 megahertz square wave looks like going into the front end of my 100 megahertz analog scope that has a system bandwidth of a little bit over 90 megahertz. Now, if I change the scale a little bit and I change that waveform all the way up to 60 megahertz, this is what it looks like. Now, notice that as we expect, it's rounded off-ish into a sine-ish wave. And that's to be expected because, like I said, we're shaving off the upper harmonics. But if you'll notice the difference between the 20 megahertz wave and the 60 megahertz wave, there's no difference in the actual amplitude, meaning that we are not cutting down in our analog bandwidth into, or past, I should say, the fundamental of the frequency, i.e. our bandwidth is over 60 megahertz. Now, to illustrate what happens when we do have our minus 3 dB point down past our fundamental, here's what our digital scope looks like in 1 times mode with the probe in 1 times mode, which, as you remember, has a bandwidth limit around like 6 megahertz-ish. So as we step the signal up past that, you get a drastic reduction in the amplitude of the signal. Now, if we switch to 10 times mode with the 10 times probe, theoretically, our system bandwidth is around 70 megahertz or so. So we should not see that lowering in amplitude until we hit the minus 3 dB point. Then we know what that is. So here is the comparison of the 20 megahertz signal in the analog scope versus a 20 megahertz signal with a 10 times probe on our digital scope. And already you can see it's a little bit more roundy-doo than we would like. But the problem was, as I toggled through the settings, I got drastically different wave shapes. And it seemed to auto-detect that and change the math accordingly. So right here, compared to that roundied off 20 megahertz signal, when I drop it down to 18 megahertz, then all of a sudden it's starting to look a lot more like we would expect it to. And we seem to get more detail on the lower nanosecond ranges than the higher nanosecond ranges, which is weird. And as you switch through those divisions and the vertical scale, you get different amplitude measurements, which is completely bonkers and you can't trust them. But if you go ahead and bump that signal up to the next notch, which is 40 megahertz, we get the much rounded off signal as we would expect, but we've also decreased the amplitude significantly. And going by the measurements on the screen, at 10 megahertz, we had a 2.06 volt signal, and then it was attenuated to 1.76 volts at 20 megahertz, and then further to 1.44 volts at 40 megahertz. And I didn't even have to go to 60 megahertz because 2.06 times 0.7, which will give us our minus 3 dB, is right around 40 megahertz, which we know because we got 1.44 volts out. But if you push through that and get up past like 60, 70 megahertz or something like that, it starts sloping up again. Then by the time you get up around 100 megahertz, you're okay. As long as it's a repetitive sinusoidal type wave. If it's like a pulse or a square wave or something like that, it just starts to completely freak out and gives you bonkers answers across the charts depending on what it is that you're measuring. Now, I don't know what exactly the bandwidth is because of the automatical features. They changed the sample rate and some of the whatever automagical math that happens in the background, presumably some of the DSP and like interpolation and all that too, depending on what variables you select as far as like the X and the Y axes. But we can definitely tell that the system bandwidth from beginning input all the way up to the output, or at the tip of the probe, as you might say, is definitely not 100 megahertz. But Alex, you just said it'll measure sine waves over 100 megahertz. Well, yeah, it will. It won't consistently measure other things over 100 megahertz. And there's non-linearities between there. Like I said, there's that bizarroness where we had a minus 3 dB point around like, the low 40s megahertz-ish, and then it started to taper up again, and then got weird like at 70 and 80, and then got fine again up around 100 for some signals. So I'm not sure what to call that bandwidth. I would like ultimately to properly test the bandwidth at each of the variable settings that changes the sample rate, rather than just giving some big blanket statement, because that's misleading depending on what you're trying to measure. And looking at the shape of the 20 megahertz signal, it seems to me that we have something a little bit higher than 40, definitely, because of the shape, or maybe there's some like automagical trickery going on in there. It's really tough to tell, and without the firmware I can't know for sure. I could just run sweeps into it and then see what I can see at a particular setting. So ultimately my hopes for this were that since it's a battery powered floating single channel high bandwidth ostensibly device, was that I could just set it up as like a permanent power supply noise recording fixture, maybe with like some custom front end tweaks or something like that. And then every time I have to measure switching noise, I wouldn't have to run it into my analog oscilloscope and spend 5 minutes fiddling knobs and kicking the trigger into balls until it does what I want it to. But unfortunately, because of the front end and the fact that we can't get down into the really small amplitude stuff, we would need a 60 decibel amplifier and a 20 megahertz limit to do that properly. And again, since we are single channel, that precludes taking the two single-ended channels, like channel 1, channel 2, running them in like parallel single-ended mode and inverting one of them to cut out the common mode noise. So that's not something that we have the possibility of doing. And when you're talking about an analog scope and using the dual channel invert one trick, you're canceling out all the noise that is common to the channels, whereas with a digital scope, you're canceling out the common mode noise, but the digital noise is additive. So you still have digital noise times 2, which is going to raise your noise floor. And if this is noisy because of the overclocked chip and some dithering in those final bits, then that would just make the situation worse. So I don't know how much more useful that would be regardless. Plus, you don't have the little selection reticles to go and measure the exact amplitudes and wavelengths of particular parts of the signal, which is really annoying, and that's present in a lot of these DSOs, so you don't get that here. But if I were to set this up as a fixture just for measuring noise, then I would probably build a custom voltage corrected amplifier, depending on like shooting in known amplitude voltages to the front end and then readjusting, making some kind of like analog, probably like a JFET amplifier up at the front, or maybe feed a JFET into a MOS or a op amp, and then program the gain so that I know what it's exactly supposed to be, and then make up a custom probe and compensate for the 2-to-1 divider or whatever that would be. Because the alternative would be buying a low voltage, low noise, high precision differential probe, active differential probe to put on the front end, and I'm not going to put a bajillion-dollar probe on the front end of like, a cheapy little oscilloscope anyway. So we'll see. Obviously, they had a different intent in mind than I did when purchasing this. But, I mean, there's still a million uses for something like this. If you're designing audio amplifiers or synthesizers, if you're doing like automotive stuff and you need a higher bandwidth, like floating battery-powered rechargeable scope, it's good for that. If you're programming DSP wave shapers or low-frequency dynamics processors, if you're looking for like lower RF oscillation and audio frequency circuits, it's fine for that. If you're just looking for like spikes, or if you're measuring like ripple in like a 60 or 120 hertz, as in like just a regular full wave rectified right off the AC mains frequency, then it's fine for that as long as the amplitude is high enough that it's considerable. But the high bandwidth or the high quoted bandwidth would make the guys want it for like higher frequency stuff. So it's not, unfortunately, as it sits, good for like high frequency switch mode power supply, like ripple noise and spikes. It's not good for any low amplitude noise. It'll get squirrely at VHF, not great for fast logic, not great for non-cyclical high frequency waves or narrow pulses. The digital storage stuff is limited, and you're not getting exact amplitudes or frequencies because they seem to shift around depending on how you're zoomed in on a signal, and I'm not exactly sure what the rhyme or the reason was for that. I haven't really poked into it, but it is annoying. So, the bad stuff. And again, this is first impression bad stuff. This could change, or the list could grow depending on like a more in-depth usage and investigation, but low-level measurements with a 10 times probe, probably not going to happen. I mean, you could put a preamp in front of it, but that's a lot of gain, man. It's likely that's from the overclock and digital noise and jitter and all that stuff. They didn't want you to go down that far. I have no idea. But again, since the firmware is not open source, we can't change it to find out. The firmware math is obviously unrefined. You can see that in the waveforms and whatnot. The bandwidth, I'm not sure what it is. I didn't test it, but it is less than 70 megahertz for the system because of the 100 megahertz probe and the 100 megahertz front end. The triggering is jittery and weird, especially on like pulses in one shot. There's no kind of manual or external or like advanced triggering modes of any kind. The single shot mode is, like I said, virtually non-existent. There's some stuff in the manual if you want to look at it. I tried a few things, couldn't get them to quite work right, so I'm just going to kind of say for now. Limited capture and storage. I mean, there is space for stuff in there, but there's nothing you can do with it except for take pictures. Firmware update, question mark, until I see some way you can get into like, DFU mode or bootloader mode or something like that. I'm going to assume that's not a thing that's going to happen. Unless one of you all finds the magical keystroke combination, then maybe we can mess with it. There's also no USB possibilities as far as like making a web front end for it that you can control on your computer, because the USB as such, the pins just aren't connected. So although you do have the programming port connected to the USB, it's basically just for charging and initial programming and presumably uploading firmware, if that's a thing that we're going to be able to do in the future. There's no 20 megahertz bandwidth limiting, which sucks because that's the specification that you use for measuring noise in power supplies. So I don't know why they didn't do that. There's really nothing simpler as far as DSP in the digital world than a low pass filter. I mean, come on, guys. There's also bizarro automagical trickery. I didn't track all the modes and test all the things, but it just kind of changed stuff on me. You can hear the relay inside clicking on and off, so I need to figure out what all that's about. And then the question of metering accuracy, like, is a meter any good if you can't trust it? And as far as I know, there was nothing in the manual about, like, when you zoom in, it does this or that and the other thing. I don't know what exactly it's measuring as far as, like, the average and RMS and that type of stuff. Peak-to-peak mode seems to pick up spikes and measure those instead of filtering them out or ignoring them, again, through DSP or just common sense. But that's not to say that it's all bad. It's just to say that it's not going to replace your desktop scope at any point in time, depending on what you're going to do with it. Now, again, if this were like, 25 years ago, I would have killed for a scope like this. But as it is today, there are options. So let's look at some of the positives. Now, it's portable. Obviously, the battery is easy to replace, which is always nice. The UI is trimmed down and a lot of the functions are tied to buttons that just deal with that function. There's not a lot of like multi-use and, like I said, not a lot of sub menus, which is something that really just annoys the crap out of me when it comes to like digital UI design. Noobs might like the automagical functions, and honestly, they are convenient for some things if you just want to toss it on something, but I don't exactly know what's going on, and it doesn't exactly break everything down in the manual. It's pretty cheap for what it is if you look at just the specs, but again, with all digital specs, scopes, the specs can be smudged and you might not even know what's going on in the background. For example, you're not getting the full sample rate when you go to particular sizes. Another positive is that you can use like real probes with it, which is nice. You're not like relegated to built-in alligator clips like some of these. And it has a built-in BNC connector, so that's nice. You don't have to use adapters or anything like that, and it's nice and rigidly attached to the device and the board. The screen is nicer than usual. It does look very nice compared to some of the cheaper ones with just like junky LCDs on them. And the case and the cover are very nice for like tossing your toolbox and things like that. There's a lot of air in there. It's not super rigid, but it should be fine for putting in your toolbox and carrying around with you. So, final impressions. It's not going to replace a desktop scope. It's not going to replace a USB-like acquisition type scope, like a Handtech or something like that. It's not going to replace a like Fluke or Handtech handheld, scope meter. But it is nicer than a lot of like the little portable jobbies that we have these days, even if it doesn't have the entire bandwidth that they say, and even if the math is a little sketchy, it's probably just as decent as those, and you have a much higher sample rate, even if I think the 500 megasamples a second might be BS. Even if it's 250, that's better than desktop oscilloscopes like 10, 20 years ago that you usually came across in like the lower price range. Although a dual channel scope or a quad channel scope would be much more useful. And while you may not be able to work with like digital stuff as well, like, you know, pulses and decoding and things like that, if you just want to toss it in your box so that you have something as a diagnostic tool on the spot for relatively high voltages, as in like logic voltages and higher than that, then it's fantastic. And if the firmware were hackable and if the hardware were a little bit more accessible, there is room in there. You do have a lot of speed on the CPU and memory and built-in DSP functions and all that kind of stuff. It could be a world destroyer. But unfortunately, I think somebody's going to step in with another type of scope with like similar hardware and pick up where you left off there. We do have the dual channel ADC that we're interleaving into like double the sample rate, but even if they're lying about the 500 megasamples and it's only 250, and you split that into 125 and 125, that could be two channels of a scope that you could say is 20 megahertz bandwidth with reasonable certainty. Certainly for sine waves, maybe even for if with some firmware tweaks for like cyclical square waves, you could recreate them, or just regular single shot square waves and pulses, as long as you don't need up to past like the fifth or sixth harmonic or something like that. You're not going to get the seventh or eighth harmonic at 125 megasamples, but you know, still decent enough. And adding in additional like triggering functions and modes, hacking it so that you can get down to like much finer vertical divisions, that would all be great. So I'm going to hang on to it and see if something like that comes around. Until then, it's going in the toolbox and it'll be whipped out if I have to go like service a guitar amp in a garage or something like that. All right, that's enough. I've said enough. I'm done, ending it right here. If you need me, I'll be over there trying to cram hydraulic tubing onto a 3D printer. Not for hydraulics, of course. That would be too easy.